Good morning to everyone. My name is Victor Ferreira Santos. I am a master's student at Universidade Federal de Santa Maria, under the supervising of Jonas Maziero. And today I'm going to talk about the main topic that we work at our group, the QAP group, Quantum Information and Emergent Phenomena, that is called Introduction to Quantum Computing, and specifically to quantum circuits. So this is the overview how this seminar is going to be conducted. First, I'm going to motivate the quantum computing panorama, and show how it's separable today in what sub-areas. And then I'm going to talk about how it works, the principles and the limitations. And finally, I'm going to talk about the one, as we will see, there are different types of quantum computing. And I'm going to talk about later the gate-based quantum computing that's based on quantum circuits. And then I'm going to talk about the framework we use to work in this type of quantum computing. So the motivation started back in 1995 with Peter Shor, that guy over there. He published this paper that he proved that there is an algorithm for a quantum computer with quantum error correction. I'll talk about that later. That if we have a quantum computer such as that, we can find, if he actually found an algorithm to find the factors of integer. So we basically found an algorithm that find the factorization of primes and non-primes. Also, later in about 4 years ago, this paper that claimed quantum supremacy. That means we have this expectation that quantum computing in the future will be stronger than classical computing, in the sense that it will solve harder problems in less time than classical computing does. So this paper actually took a problem and solved it in way less time. I don't recall the exact time, but I think it was about 1,000 years, something like that, for classical computing. And in this paper with quantum computing, they solved that problem within weeks. So it was a claim that quantum supremacy is already beginning. And finally, last year, this paper, which claimed that they built, it's not exactly a wormhole, but they created some system that resembled a wormhole in a quantum computer. So this is, there are a lot of other papers, but this is, I think, in the past 20 years, the most important to motivate quantum computing. So this is basically how it's separated today. It's a very good visualization. So first we have the construction of quantum computing. How are the principles used to actually build quantum computing? The applications and the different panoramas of quantum computing, as I'm going to talk about soon. So this is a very good map, and it shows that quantum computing is very complex and very big, in the sense that there is a lot of things to be studied yet. So how does it work? Mainly, there are three principles that are important for this for quantum computing, which are superposition, when you have for example, a system that can be in multiple states at the same time, and contrary to the classical panorama, which doesn't make any sense in classical physics, but in quantum physics this is possible, and this is one of the principles that are present at quantum computing panorama. So another one is entanglement, that we have, for example, two or more systems that have can have stronger correlation than classical ones. So, for example, you take the Bell states. That means if you have two qubits, I'm going to talk about briefly soon about qubits, but just take as quantum system. You take two qubits and you entangle them in such a way that you get what we call a Bell state. And this Bell state is the strongest relation. It's the maximally entangled state for this type of system. And you can show that this is a correlation that is stronger than any classical correlation. So this is fundamental for quantum physics and also present in quantum computing. And finally, interference, that I think everyone here is familiar with, that we associate wave phenomena with probability densities. This is more important in the construction itself of quantum computers, how they transmit information and change states. So this is the main principles here. So after we get these principles, there are many types of quantum computers that we can build. One of them, which I'm going to talk about in this seminar, is gate-based quantum computers. It's basically you have superconducting qubits, and they are manipulated through logic gates. So in analog way to classical logic gates of classical computing. This is very analog in the way that we get similar gates. Another one is diabatic quantum computers, which is basically used to solve optimization problems. It's really new compared to gate-based quantum computers, and they operate under the quantum annealing effect, which is when you have continuous transformation of a state, you can actually maintain the same state you start with. If you start, for example, with 0 point state and you apply a continuous transformations, it is possible to show, there is a theorem called the Qiskit theorem, that this state will be maintained throughout the evolution. This is quantum annealing. So finally, topological quantum computers is, I think, one of the most recent. Microsoft is working on it, and it's not actually qubits, which we use. It's actually anyons with R2D particles. There are many others quantum computer panoramas, but this is, I think, the most important ones. The limitations. You have errors, such as in classical computing. This is an example. We have two types of errors, and this color light orange means that these two qubits will identify the error in the red qubit, and the other, for the bit flip error, the dark orange will identify. So this is a type of quantum error correction, and this is what we need in the future to have better quantum computers. So how do we compare with classical computing? It's actually pretty simple if you understand quantum physics. Bits can only be in 0 or 1 state, but in quantum computing you have, as I said, superposition. So for example, a bit can only be in 0 or 1, as you can see in the image, but a qubit can be a infinite superposition, infinite combinations of superpositions. And this is actually one of the advantages we think that will be really important for better quantum computers. And you have gates, which in classical computing mean there are 8 classical logic gates, and they simply take 1 or 2 bits and they convert to another based on Boolean logic. It's actually very simple, but in quantum gates, you have a lot more, and they have this property. They should be unitary, which means that they must be reversible, because we need to preserve probabilities. So There are many X, Y, Z are the Pauli gates, very famous. One of the first things we see in quantum physics. And when you have these gates, you can actually build circuits. For example, these classical circuits, there are two gates, and then they take B and C for one gate and A, B for another. And based on the values of B, C, and A, B, they produce two other bits. And again, you apply another gate at the end, the most right one, and then you have another result. Contrary to classical logic gates, for quantum computing, you have, for example, this H block means it's a Hadamard. It's a gate that creates superposition. For example, if I start with qubits in 0 state, Hadamard creates a superposition of 0, 1 with equal probability of 1/2. As you can see there with the square root of 2 factor. So you can see this is actually the Bell state, one of them. And well, when you have this gate-based panorama to quantum computing, you have actually tools to help you. IBM's Qiskit, which means quantum information kit, is a framework that is based on Python. So you can actually create circuits through Python coding, and there are two options. You can make simulations that, of course, since it's a simulation, you'll be making it in your classical computer, since this Qiskit is based on a cloud, coding, so you can use your own computer to make simulations. But in the future, right now, simulations are better, but in the future, we expect experiments to be better because they are actually performed on quantum computers. So since we have this expectation of better quantum computers being better, so experiments being made on actual quantum computers in the future will be better. So you can actually use IBM's Qiskit to perform experiments on their quantum computers. This is, of course, we have a limitation for free users. I think it's 7 qubits. And you have to get you have to wait for other people to use it. First, you get in the como é que é fila em inglês? Como? Fila. You have to get into a queue and wait for a time. So you send your code to IBM's Qiskit, and then after you get in the first place of queue, they will return your results. This is an image of a quantum circuit I'm actually implementing in my work. I talked in the last seminar that I need, if you recall, if you were here, I talked that I need about needing the estimation of the purity, which is the trace of the density operator squared. This is actually one circuit we found out that can do that. So this is just an example of how strong quantum computers can be, and in particular this Qiskit tool that we have. Thank you very much.